The moon is the closest celestial body to Earth, yet it remains one of the least understood. On December 1st, 2020, a Chinese lander touched down on the lunar surface. For the first time in space exploration history, it extracted samples from deep beneath the moon's surface. These rocks turned out to be 1 billion years older than anything ever brought back by the Apollo missions. This isn't just a number on a timeline. It cracks open the very foundation of what we thought we knew about our satellite. And just months before, on the far side of the moon, the side we never see from Earth, a Chinese rover stumbled upon a substance that scientists still can't fully explain. The Chang'e 5 mission launched from the Wenchang Space Launch Site on Hainan Island, China's main hub for lunar missions. This same launch site sent cargo ships to China's orbital station and previous Chang'e missions into space. The probe, weighing about 8 tons, had a single clear goal: land on the moon, collect soil samples, and bring them back to Earth. No one had managed such a feat in 40 years. 40 years. Not a single gram of lunar rock. They didn't choose the landing site by chance. Oceanus Procellarum is a vast basaltic plain near the lunar equator, right next to Mons Rumker. Geologically, it's one of the youngest regions on the moon. Well, relatively young. On lunar timescales, young still means billions of years old. But here, calculations showed that beneath the layer of dust and debris lay rocks untouched by any mission before. The lander's drill reached below the surface, where no instrument from any previous mission had ever reached. The Apollo missions collected rocks and regolith from the surface. Soviet automatic stations did the same. Chang'e 5 was the first to pull material up from deep underground, and the age of this material didn't match anything found in labs around the world. But Oceanus Procellarum is the near side, the side always facing Earth. On the far side, hidden from every telescope on Earth, something even stranger was happening. The Yutu-2 rover was rolling across the floor of the von Karman crater when its camera captured something unusual. On the gray, dusty lunar soil, there was an orange-yellow patch. It looked gel-like with a moist sheen. On the dead, dry, airless moon, this was a substance that appeared freshly spilled. The very fact that the rover operates on the far side of the moon is an engineering feat all on its own. The moon blocks any direct radio signal from Earth. Total silence. The rover over there is like a phone trapped in a bunker. It has data, but nowhere to send it. China's space agency solved this problem with a relay satellite orbiting beyond the moon, bouncing signals back to Earth. Without this single relay, every photo from Yutu-2 would have remained just a set of electric impulses stored deep in the rover's dead memory. No one would have known. And so, through this fragile thread of connection, that photo of the orange gel arrived on Earth. Western scientists, lacking detailed data from China about the composition, offered the most familiar explanation: impact glass. When a meteorite slams into the surface, the rock instantly melts at thousands of degrees, then solidifies into a glassy mass with an unusual color. We've found this before. It's a convenient, logical explanation. But the exact nature of the material remains unconfirmed. China hasn't released a full chemical analysis. Visually, this gel doesn't resemble any impact glass described in scientific literature. Science tried to make sense of the anomaly using the closest known term. Did it work? That question remains open. Here's what unfolds. On one side, a drill pulls up rock from the moon that's an entire geological era older than expected. On the other, a camera on the far side captures a substance that science can only tentatively explain. Two signals from two different points on the same world, and both tell the same story. We know far less about the moon than we thought. But before that drill bit sank into the ancient rock, scientists were absolutely certain about what the moon could not possibly contain. Water. There can't be water on the moon. This isn't just a theory or a guess. It's a direct consequence of physics. locking the moon in a dry state with no key to unlock it. The moon's surface barely holds an atmosphere. The pressure there is 10 trillion times lower than Earth's. Temperatures swing wildly, from a scorching 127 degrees Fahrenheit on the sunlit side to a freezing minus 173 degrees in the shadows. At such low pressure and extreme temperature shifts, liquid water simply can't exist. It either evaporates instantly or sublimates, turning directly from ice into vapor without ever becoming liquid. No rivers, no lakes, no puddles. Not a single drop. Here's the crucial point. This isn't a temporary state. The moon's density is too low to hold on to any kind of gaseous envelope. Its magnetic field is so weak that the solar wind blows away any volatile molecules from the surface without resistance. These conditions won't change in 1,000 years, or 1,000,000. The moon is a locked door for good. Trying to terraform it to create a hydrosphere is like trying to fill a colander with water in open space, and that naturally invites a comparison with its nearest neighbor. Mars once had flowing liquid water. Dry riverbeds and erosion patterns visible from orbit prove that. Mars at least has a thin atmosphere, polar caps made of carbon dioxide and water ice, and real plans for terraforming. Mars is a tough challenge, but it's a challenge nonetheless. The moon, on the other hand, is the problem itself, with no solution. A dead rock, completely dry, period. Here's a useful rule. When everyone thinks the question is settled, that's exactly when you should check who closed it, and when. Confidence in an answer can sometimes stop us from asking the right question. On December 17, 2020, a return capsule landed in the snowy steppes of Mongolia. Small, blackened from atmospheric entry, weighing just over 300 kilograms. Inside, about 1,700 grams of lunar soil brought back by the Chang'e 5 mission. They found the capsule, opened it, and sent the samples to the laboratories of the Chinese Academy of Sciences. Testing began. The usual routines: mineral composition, rock age, grain structure. But that's where routine ended. When scientists placed the samples under an electron microscope, they spotted something unexpected. Tiny glass beads appeared, spheres just tens of micrometers across. To put it simply, each one was several times thinner than a human hair, and there were a lot of them. Not just isolated specks, but densely packed throughout every gram of the sample. The process behind their formation is clear. When a meteorite slams into the lunar surface, the rock instantly melts at temperatures reaching thousands of degrees. The molten material sprays out, cools rapidly in the vacuum, and solidifies into these microscopic glass spheres. Over billions of impacts across billions of years, the entire lunar soil becomes peppered with them, like raisins scattered through dough. At first glance, it might not seem groundbreaking. Scientists had found impact glass before, even in samples brought back by the Apollo missions. But researchers at the Chinese Academy of Sciences decided to do more than just catalog these tiny beads. They looked inside them. What they discovered in the structure of these microscopic glass capsules didn't fit the model of a completely dry lunar surface. Physics says water can't exist on the moon's surface. This has been proven, recalculated, and confirmed countless times. Yet these glass grains, forged in the fiery blasts of meteorite impacts, held inside them something that shouldn't be there. Water, trapped inside glass, on a dead, airless, radiation-baked surface where every water molecule exposed should instantly vaporize into the vacuum. And yet, there it is, detected by a spectrometer, concentrations reaching up to 2,000 parts per million. A tiny number when you look at a single bead, but there are billions of these beads packed into every gram of regolith. Here's what really matters. The samples collected by Chang'e 5 are about 1 billion years older than those brought back by the Apollo missions. The drill went deeper, pulling rock from much older layers. That means the water locked inside these glass capsules hasn't been there for just tens or hundreds of millions of years. It's been there since a time when not a single multicellular organism existed on Earth. And it's still there, sealed tight like a microscopic bottle with an airtight cap. But how did it get there in the first place? The surface of the moon has no atmosphere, no liquid water, nothing that could deliver hydrogen and oxygen in the right balance. Could comets be the source? Maybe, but a comet is a one-time event. Yet water here spreads evenly, everywhere, as if someone has been methodically injecting it for billions of years. And in fact, someone has been injecting it, the sun. Researchers have uncovered a mechanism that might be the most elegant chemical reaction in the entire solar system. The solar wind, a stream of charged particles, mainly protons, which are hydrogen nuclei, bombards the lunar surface non-stop, every second, without pause, without a break. These protons slam into the moon's upper layer of regolith and encounter oxygen locked inside lunar minerals, silicon oxides, titanium, iron. Hydrogen meets oxygen. The result? Water molecules that get instantly trapped inside tiny glass microspheres, like miniature safes. In simple terms, the sun acts as an endless water delivery system. It supplies the hydrogen, the lunar soil gives up the oxygen, and the glass seals the final product. It's as if rain doesn't fall from clouds, but straight from sunlight itself. Only instead of drops, there are individual molecules, and instead of puddles, there are sealed glass beads thinner than a strand of hair. Now, let's talk numbers. Calculations suggest that each metric ton of lunar soil could hold up to 2,000 kilograms of water. That's 2,000 liters. Imagine a metric ton of soil roughly the size of a desk, if the desk were made of densely packed lunar sand. And inside that volume, 2 tons of water. It sounds incredible, but this estimate comes from measuring water concentrations in tiny beads and how densely they scatter throughout the lunar soil. The total amount? Around 299 billion tons of water spread across the entire lunar surface. Not just in one crater, not only at the poles, everywhere. This isn't some hidden lake waiting to be discovered. It's a sponge we're already standing on. And here's what makes this discovery truly practical. To extract water from the glass beads, you don't need a centrifuge, a chemical reactor, or pressure reaching hundreds of atmospheres. All it takes is heat. Simple heat. The glass releases water as the temperature rises. Molecules break free from the crystal lattice and gather as vapor. You can do this anywhere on the moon. Not just in the permanently shadowed craters at the poles, where landing alone is an engineering feat, but right where it's easier to build a base. Polar ice, the target of decades of searching, matters. But it turned out to be only one source. Water was everywhere, right beneath our feet, trapped inside glass formed by meteorite fire and charged by the solar wind. A process no one expected was happening in plain sight, literally on every square meter of the surface. But water is a matter of survival. Fuel, oxygen, drinking water, the basic needs of any outpost. The real shock came when scientists moved beyond glass beads and started analyzing the crystal structure of a completely different substance, a mineral that had never appeared in any Earth catalog before. Michio Kaku, a theoretical physicist, best-selling author, and one of the most recognizable science communicators in the world, goes on air and reveals something Beijing isn't ready to announce yet. The Chinese have discovered a helium-3 crystal on the moon. There's no official press release, no coordinated statement, just this famous American physicist saying it out loud, and the news spreads before anyone can even prepare it. The China National Space Administration finds itself in a position where staying silent no longer makes sense. They confirm it. Let's pause here to focus on what exactly was discovered. Within the lunar rock brought back to Earth, scientists found a phosphate mineral unlike any listed in the world's catalogs. This marked the 6th new mineral ever identified on the moon, and the very first discovered by China. They named it Chang'e Yi, honoring Chang'e, the Chinese goddess of the moon. It's a tiny, column-shaped crystal just about 10 micrometers across. That's 10 times thinner than a human hair. You can only see it through an electron microscope, a transparent column barely visible against the gray lunar soil. But inside this tiny pillar lay something with the potential to transform the energy landscape of an entire planet. Scientists found helium-3 in the crystal lattice of Chang'e 5's lunar samples, a rare helium isotope that's almost non-existent here on Earth. Our planet holds only a few kilograms of it, but on the Moon, where there's no atmosphere or magnetic field, the solar wind has been embedding helium-3 into its surface for billions of years. And this is why it matters. Fusion, the process that powers the sun, fuses light atomic nuclei together. Unlike nuclear fission, which splits heavy atoms like uranium and plutonium, fusion joins light nuclei, releasing vastly more energy. It doesn't rely on a chain reaction that can spiral out of control. It doesn't produce tons of spent fuel that remain radioactive for centuries. Simply put, fusion offers clean energy without the long-lived radioactive waste. It sounds like a solution to all our problems at once, but here's the catch. Humanity has wrestled with controlled nuclear fusion for more than 70 years, and not a single reactor has ever produced a net gain. To force atomic nuclei to fuse, you have to heat plasma to 150 million degrees. That's 10 times hotter than the core of the sun. Holding that plasma in place is like trying to squeeze a star into your palm. Magnetic traps as large as a 5-story building. Superconducting coils chilled to nearly absolute zero. And all of this just to sustain a reaction for a few seconds, one that consumes more electricity than it generates. The input costs consistently outweigh the output. We've hit an energy dead end. And this is where the real mystery of the lunar crystal begins. Helium-3 changes the game. When deuterium fuses with helium-3, the reaction happens at lower temperatures. It doesn't produce a stream of neutrons that eat away at the reactor walls. Instead, it releases energy in the form of charged particles, energy we can capture directly without bulky steam turbines. In other words, this fuel burns cleaner, ignites more easily, and won't turn the reactor into a radioactive wreck after just 10 years of use. While helium-3 is nearly non-existent on Earth, the lunar soil, soaked in solar wind for 4.5 billion years, holds a reservoir humanity has just touched for the first time. Samples containing helium-3 were sent to the Beijing Institute of Uranium Geology. Not to a general science academy, not to a university lab, to an institute that specializes in nuclear fuel. That choice speaks louder than any press release. China never intended to just put the crystal on a shelf. They saw it as a valuable resource. And here's what hung in the air after all the confirmations and press conferences. If fuel for nuclear fusion really lies on the moon's surface, whoever masters the extraction and transport will hold the key to the global energy market. And a key of that magnitude never stays a matter of science alone. $3 billion. That's the price for just one short ton of helium-3 extracted from the lunar surface. Not a barrel, not a cubic meter. 1 ton equals 907 kilograms. To put that in perspective, a ton of gold, at the time of this recording, cost about $60 million. Impressive, right? But gold is about jewelry, electronics, and bank reserves. Helium-3, though, that's energy. And here, the numbers take on a truly daunting meaning. Let's do the math. The United States is the largest economy on the planet. Power plants, factories, server farms, air conditioners in 330 million homes. How much helium-3 would it take to power all of that for an entire year? 1,000 tons? 10,000? Experts estimate 27.6 short tons. That's about 25 metric tons. It's an amount that fits inside the cargo bay of a single space shuttle. One trip, and a country with 300 million people gets electricity for 12 months. Now multiply 27.6 tons by $3 billion per ton. That adds up to just over $82 billion. Is that a lot? The United States' annual energy budget runs around $1.5 trillion. The difference is 18 times less. This isn't just cheaper, it's a whole new economic reality. Here lies the biggest mystery. Not a scientific one, a geopolitical puzzle. If a resource this valuable exists, and one country is the first to build the infrastructure to extract and deliver it, what will happen to the global energy market? China didn't hand over the lunar samples to a university, nor to an academy of sciences. They sent them to a nuclear fuel institute. And here's what that means, translated from diplomacy into economics. China, by recognizing helium-3's potential first, could seize a dominant position in the world energy market. Not an oil dominance, temporary, fragile, reliant on wells that will run dry, but a fusion-based dominance that could last for centuries. The country controlling access to lunar helium-3 controls energy itself, and whoever controls energy sets the rules for everyone else. This isn't speculation. It's a model the world has already lived through with oil in the 20th century. Only this time, the stakes are even higher. Private industry understands this clearly. Major energy corporations have already shown interest in investing in future NASA missions aimed at tapping lunar resources. This isn't charity or scientific curiosity. It's cold, hard calculation. Yet between interest and profit lies a vast chasm, one no one has crossed. To mine helium-3 profitably, we need a complete supply chain. Mining operations on the lunar surface, processing plants capable of extracting the isotope from millions of tons of lunar soil, and, critically, affordable, reusable spacecraft that can make the Moon-to-Earth route as routine as a cargo flight across the Atlantic. None of these pieces exist yet. Each demands decades of development and hundreds of billions in investment. The gold rush has begun, but the mine itself hasn't even been built. Discovering helium-3 turns the Moon from a mere target of scientific missions into a battleground for economic power, one that could redraw the map of influence on Earth. Space programs from dozens of countries and corporations no longer chase abstract knowledge. They seek control. But to extract these billions, humanity faces a challenge it has never truly tackled before. How do we live and build where the ground is nothing but dust, and above us, there's only emptiness? The answer lies right beneath our feet, literally. That very lunar dust, the regolith that gums up machinery and scratches helmet visors, has turned out to be a building material. Moon soil can support the construction of bases and protective structures. Several companies have already developed three-dimensional printers that can sinter this fine-grained gray powder into ready-made blocks for walls, ceilings, and laboratory modules. You bring the printer once. The raw material is everywhere around you, just a few meters deep. But you can't live inside printed walls without air, and here, in my view, is the most elegant part of lunar engineering. You can extract oxygen and water from that same regolith. The European Space Agency has already perfected this technology. Heat the rock, break down metal oxides, and you get breathable gas. In other words, lunar dust itself becomes both brick and air at the same time. Oxygen is also half of rocket fuel. There are plans to build an oxygen pipeline from a processing plant to the future lunar base of the Artemis program. A pipeline. On the Moon. It sounds like a line from 60s science fiction, but the engineering calculations are already on the table. And the pipeline isn't the only source. In the polar craters, where sunlight hasn't reached for billions of years, temperatures stay below minus 230 degrees Fahrenheit. Estimates suggest up to 600 billion kilograms of water ice lie hidden there. 600 billion. That's about 240,000 Olympic-sized swimming pools, frozen in darkness at the bottom of craters where there has never been wind or sound. Water for drinking, water for electrolysis, water for fuel, all in one place. But energy isn't just about surviving on the surface. Helium-3, which we mentioned as a potential terrestrial energy source, could also fuel fusion engines for spacecraft. These engines would enable longer missions with heavier payloads, while cutting costs. Suddenly, the Moon stops being the final destination. It transforms into a refueling station on the way to deep space. And this is where we need to pause and look back. China's roots in rocketry stretch all the way to the 9th century, when gunpowder arrows, hissing through the air with fiery tails, became the first primitive rockets in history. From those came fireworks. From fireworks came the principle of jet propulsion. Over 1,000 years passed, from bamboo tubes filled with gunpowder to the complex dance of orbital mechanics. Modern space exploration for China began in the late 1950s, closely working alongside the Soviet Union. But that partnership eventually fell apart, and China went its own way. On April 24, 1970, it launched its first satellite. Then, in 2007, came the lunar orbiter named Chang'e-1. The following year, 2008, marked China's third crewed mission with Shenzhou-7. Today, China operates its own multi-module space station, rivaling the International Space Station, and plans to expand it further. 11 centuries separate these milestones, from a gunpowder arrow to a modular station orbiting Earth, from a spark inside a bamboo tube to a regolith printer and oxygen pipeline on the surface of another world. Here's the paradox running through this entire story. To break free from Earth, humanity had to learn to use what lies beneath our feet. Gunpowder from the ground, kerosene from the ground, and now regolith, ice from shadowed craters, helium from lunar dust. We don't conquer space in spite of matter, we conquer it because of matter. Every time, a new soil, a new fuel, a new leap. The moon isn't the finish line. The moon is the shore, where you can see an open ocean beyond. And for the first time in history, those standing on that shore have a map, a ship, and, most importantly, fuel they don't have to haul from home. 1,000 years ago, spark in bamboo, the hiss of gunpowder, an arrow flying into the night sky. Today, the silence of vacuum, white dust underfoot, and 600 billion kilograms of ice waiting in the crater's dark. Between them, the same dream, to rise higher. Only now, we have the means.